Hello, my name is Shahriari, and this is a lecture in a series of lectures on linear algebra based on my book, Retrolinear. In this lecture, we talk about systems of linear equations. We will also introduce elementary row operations and reduced row echelon form for solving systems of linear equations. We'll talk about what we mean by a system of linear equations, then elementary row operations, reduced row echelon form, and then basic and non-basic variables and how to write down the solutions to a system of linear equations. Here's an example of a system of linear equations: x minus y plus 2z minus w equals minus 1, and three more equations. System, it could be one equation, but it could be more than one equation. And when we have more than one equations, like here we have four equations, we don't want to solve each one of them individually. We want to find solutions that satisfy all four at the same time. So we want to find x, y, z, and w that satisfy all four equations, and that's called a system of linear equations. The reason it's called linear is that the variables x, y, z, and w, the unknowns, the guys that we're trying to find, are here linearly. So what that means is that we have x, we have y, we have z, we have w, and they have coefficients which are constants, like a 2 and a minus 1 and a 3. But we don't have anything of the form x squared, or x times y, or tangent of y, or e to the x, or 1 over w. All the unknowns come in the form of just themselves multiplied by a constant, and then we're adding them and equating them to a constant. And that's what a linear equation is. Later on, we will have a more conceptual way of saying what a linear equation is. Not in this lecture, but later in linear algebra lectures. And what's the solution to this? The solution to this means that I have to find x and a y and a z and a w that satisfy all four equations at the same time. It's not enough to just find solutions for one of them. You have to find solutions that work for all of them. For example, if you put x, y, and z equal to 0 and w equal to 1, you can check that all four equations work. So that's one solution to the system. One solution to this system consists of four numbers: an answer for x, for y, for z, and for w, such that all four equations are satisfied. That solution doesn't have to be unique. The system doesn't have to have solutions, but if it does, it might be that there's just one solution, but it might be that there's more than one solution. In this particular case, for example, x equals 47, y equals 94, z equals 47, and w equals 48 is another solution. On the other hand, if you put all of them equal to 1, x, y, z, and w, that's not a solution. There's plenty of combinations of x, y, z, and w that are not solutions. There are some, more than one, possibly infinite combinations that are solutions, and we are trying to find those solutions. Our basic idea is that we want to find equivalent but progressively simpler systems. We want to start with this guy, and we want to manipulate it until it becomes simpler, and then that simpler one we want to solve. We want to make sure that along the way we don't change the solutions. So when we manipulate the system and make it simpler, we want it to get a system that doesn't have any fewer solutions or any extra solutions from the one we have. We limit ourselves to three types of moves. We could have other moves. It's not like these are the only moves that will not change the solutions to our systems, but these three moves are enough, and they certainly will not change the solutions to the system. You can think of it as a game. We only have three types of moves that we are allowed to do. So what are they? One of them is that we are allowed to switch the place of two equations. That clearly isn't going to change anything, and it sounds silly. If I like that fourth equation a lot, I can bring it to the top if I want to. I can also multiply an equation by a non-zero constant. For example, again, look at that last one, 3x minus 3w equals minus 3. I could multiply through by 1/3. That's the same as dividing by 3. I get x minus w equals minus 1. If I replace 3x minus 3w equals minus 3 by x minus w equals minus 1, solutions to that new system will be the same as solutions to the old system. The last move is a little bit more complicated. You pick your favorite equation, and then you're going to add a constant multiple of another of the equations to it. For example, I might take the third one, multiplied by 1, which means that I didn't really do anything to it, and then add it to the first one. So what does that mean? X minus x, that goes away. That's probably why I did it, to get rid of the x's. Minus y plus 2y, I'm adding the third one to the first one. Minus 1 plus 2y will be y, and so forth. The right-hand sides will be added too, and 1 minus 1 will be 0. So I'll get a new equation, and I'm going to replace my original equation, the first equation, by this new equation. You replace your favorite equation by adding the constant multiple of another equation to it. Why doesn't these things change the solutions to the system? Is because actually all three moves are reversible. No information is lost. If you didn't like what you did, you can always go back. So if you switched and you didn't like it, you can switch back. If you multiply it by a non-zero constant, you can multiply by its reciprocal, and you're back to where you started. If you added 5 times an equation to another equation and you didn't like it, add minus 5 times that first equation to this one, and you will be back where you started. Because things are reversible, there's no information lost, and the solutions to one system got to be the same as the other. We'll give a much cleaner formal proof of this in a later lecture. But if you think about it a little bit, it should be intuitively clear that you do not change the solutions to this system at all. You don't add or subtract anything if you just use these moves. Instead of doing those operations on the equations, which is a little bit cumbersome, we switched to a matrix. In a previous lecture, we gave some of the vocabulary for matrices, but here we're going to just use them. A matrix is just a rectangular array of numbers. We're going to take the x, y, z, and w out, and we're going to just look at the coefficients. There's no information lost here, so I'm going to have a column for each one of the variables, x, y, z, and w, and a column for the right-hand side of the equations. And then for each equation, I will have a row. For example, the first equation was x minus y plus 2z minus w equals minus 1. X had coefficient 1, so I'll put 1 there, and then minus 1, because minus 1 was the coefficient of y, 2 was the coefficient of z, minus 1 was the coefficient of w, and then minus 1 was the right-hand side. We put all the coefficients into this matrix. This matrix is called the augmented matrix for the system of linear equations. We don't keep the headings. We are thinking that that second column are the coefficients of y, and that fourth column is coefficients of w, and the third row is equation 3, but we don't keep that information. We just keep the augmented matrix. And this is the object on which we'll perform those moves that we talked about. And those moves are called elementary row operations. Multiply a row by a non-zero constant, interchange 2 rows, and replace one row with the sum of that row with a multiple of another row. These are called elementary row operations. These are things you do to a matrix. You might do these to a matrix even if that has nothing to do with solving a system. These are elementary row operations on a matrix, the ones we are going to use to solve a system. Now, the question is that what should our goal be? How simple can we or should we try to make the matrix? How far should we take this? What we want to do is to arrive at something called the reduced row echelon form of the matrix. RREF. We are given a matrix and then we do these elementary row operations, maybe a million of them, until we get a form that we really like. And that form is called the reduced row echelon form of that matrix. Let me tell you what the reduced row echelon form of a matrix is. This matrix C, for example, is a 5 by 7 matrix, and it happens to be in reduced row echelon form. So this is the kind of matrix that we want, but I've got to tell you, what do we mean by that? A matrix is in reduced echelon form if certain conditions are satisfied. The first one is that if the matrix has a row that has all zeros in it, that should be at the bottom. This matrix has 2 rows of zeros, and they're at the bottom. If it doesn't have a row of zeros, then you don't have to worry about this rule, because then it's automatically satisfied. But if you have a row of zeros, you want to shove them at the bottom. One of the elementary row operations was switching rows. If the row of zeros was somewhere else, you can certainly bring it down. The rows that are not a row of zeros, so they have numbers in them, if you start from the left-hand side of that row, the first thing you should get to is a 1. So it should be zeros and then a 1, and then whatever afterwards. That 1 is called the leading one. It leads the row. It's the first thing you get to. Another name for it that I sometimes will use is a pivot. Those leading ones are called pivots. These leading ones should be staggered to the right. So that means that each leading one should be to the right of the leading ones prior to it in the higher rows. As you're coming down the matrix, you are going to the right. One final thing. Every column that has a leading one, not all columns have leading ones, all the other entries in that column have to be zeros. For example, the fourth column has a leading 1, and everything else in that column is 0. The same with column 2 and column 7. There's 3 leading ones, and those columns have zeros everywhere other than that leading 1. Other than these rules, we don't have any other rules, and that's why there are some random numbers like 3, 4, 5, 2 minus 1 in the matrix, and that's okay. That's still a matrix in a reduced row echelon form. This is our goal. We use elementary row operations to get our matrix in this form. The point is that using elementary row operations, you can transform any matrix into a matrix in a reduced row echelon form. There is a systematic algorithm, step by step, called the Gauss-Jordan Elimination for doing that. The Gauss-Jordan Elimination first came about by Gauss, who was an 18th century mathematician, and Jordan later on made some additions to it. But an almost identical method was already in the book, The Nine Chapters, a Chinese classic from 2nd century BCE, a long time ago. And so I'm going to call it the method from the 9 chapters. Not that Gauss knew about that, but it just seems the 9 chapters had a 2,000-year head start on Gauss. So what is this? You start with a matrix, you're going to do elementary row operations, and you want to get it in reduced row echelon form. I'm going to tell you the steps here, but really the proof of the pudding is in the eating. When I show you the example, you'll know what I'm talking about. You start from the top left and you go down. And each stage you're trying to find the pivot and use it to do stuff. First, you find the leftmost column with a non-zero entry. There might be some columns with all zeros. Ignore those. Bring a non-zero entry to top of the column. You can do that by switching rows. Then turn that top non-zero entry to a leading one. How do you do that? By multiplying by a constant. So if it's a 5, you multiply by 1/5. If it's 1/5, you multiply by 5. You make it into a 1. Then you use that third elementary row operation and that leading one to turn everything else in that column to 0. Now you repeat, you ignore the rows that now have a leading one and you figure out where the next pivot is. Then repeat the other steps. One piece of notation before I give you an example. If A is a matrix and R is the reduced row echelon form of A, then we write R equals RREF of A. So A is some complicated matrix, you bring it into this reduced row echelon form, and then you call that, whatever you got, RREF of A. Now let's look at an example. Here's our original example. We make the augmented matrix. And again, we're thinking that the columns are associated with the variables and each row has to do with one of the equations. And the line that we put between the 4th and the 5th column is to show that the first columns are related to a variable, but the last one is the right-hand side. If you don't put that right-hand side in, then the thing that we get is called the coefficient matrix. Step 2 is to use the method from the 9 chapters, Gauss-Jordan Elimination, to find the reduced row echelon form of A. Here's my matrix. The first thing I do is I look at the first column that has some non-zeros in it, and that's actually the first column. The top element is 1. So that's my pivot. As soon as I have that leading 1, I know I've got a pivot, I've got a leading 1. I use that to make everything else in its column 0. How do I use that 1 to make that 2 0? I multiply that first row by -2. I don't write that anywhere, but then I add that to the second row. I'm switching the second row out, and instead of it, I'm putting minus twice the first row plus the second row. You get this. So -2 times 1 is -2 plus 2. That's 0. That's what I wanted. -2 times -1 is 2. 2 plus 1 is 3. That's why in the second row of the new matrix, I have a 3. -2 times 2 is -4. -2, that's -6, and so on. The second row became 0, 3, -6, 0, 0. All I care about is that row 2, column 1 entry. Instead of 2, now I have a 0. Now I do the same thing for the other entries in that column. For example, how do I change that -1 in the third row, first column into 0? I multiply the first row by 1 and then add it to that row, and that makes that 0. And I multiply the first row by -3 and add it to the last row. Note that when I'm saying multiply by -3, I don't actually change the first row. The first row is not changing anymore. I'm just adding a multiple of that row to other rows and changing those other rows. This is what I get. Our next step is that I ignore that first row because it has a leading 1 and look at the rest of the matrix. And I say that what I need is a new pivot. And so that 3 is the one that I've got to focus on. I could now switch the third row and the second row and make that a 1 if I wanted to. That's a possibility. Or I can just make that 3 into a 1 by multiplying by 1/3. And that's what I did. This is what I get. One advantage of doing things on video is that numbers turn out nice. When you're doing homework, sometimes you get a lot of fractions. But trust me, if you give a lecture, often the numbers come out really nicely. That's just the way gods work. So that's your leading 1. Now that you have a new leading 1, you use that to make everything else in its column, including that top -1, 0. Because we have all those zeros that we made before, we're not going to mess with the first leading 1. And this is what you get. At this point, you're done because you have a matrix in reduced row echelon form. Why did we do any of this? Because we started with a system and these moves are not changing the solution to the system. So now we have a new system, and this new system has exactly the same solutions as the old one. But the new system is actually much easier because 2 of the rows are all zeros. We have got 4 columns, x, y, z, and w. What are these equations? And these equations are x minus w equals -1 and y minus minus 2z equals 0. Much simpler than before. Our method isn't done yet. We're not going to haphazardly decide what to do. We still have a method to our madness and what we're going to do here. We're going to notice that because every non-zero row has a leading one, that variable is just appearing as itself. Like x is just x here. There's no 2x or 3x or minus x. And that x is appearing only in one equation because of the fact that in the columns with the leading ones, everything else was 0. And the x and y are the ones that have a leading one in their column, and they appear exactly once. Solving for them is really easy. And so we're going to make a distinction between the variables that have a leading one in their column and the ones that don't. A is an augmented matrix of a system of linear equations. R is reduced row echelon form of A. We started with the matrix and then we found the reduced row echelon form of A. The variables that correspond to the columns with leading one in R are called basic variables, and the other variables are called non-basic variables. Step 3 for solving systems of equations is to say that each of the non-basic variables can be an arbitrary real number. You can choose those to be anything you like, and you can solve the basic variables in terms of the non-basic variables. Non-basic variables can be anything you like, and then you find the basic variables in terms of the non-basic variables, and that's actually very easy to do because of the fact that those just appear in one equation and with, in fact, the coefficient of 1. In our situation, this is what we had. We had x, y, z, w, and x and y were basic variables, and z and w were non-basic variables. This is the system we're trying to solve. X minus w equals minus 1, and y minus 2z equals 0. That's what I'm reading from the reduced row echelon form of my matrix. What I do is that I say that z and w, the two non-basic variables, can be an arbitrary real number, and I'm giving them names. You could actually keep them as z and w if you like, but I'm going to call z s, some arbitrary real number, w is t, an arbitrary real number, and then x is going to be t minus 1. Likewise, y equals 2z. So if z is s, y will be 2s. And now I've got all my solutions. There's infinite number of solutions. You get to pick your favorite s and t. You could pick both of them to be 0, for example, and that will tell you that x is minus 1 and y is 0. Or you can pick z to be 47, w to be 98, and then figure out what x and y is, and you will have a solution to that original system. One final thing, how we are going to write the solutions. We had this system and we got all the solutions. One way to present the solutions is what I had earlier. Another way is to present the solution as a set, as t minus 1, 2s, comma s, comma t, where s and t are real numbers. This is set notation. Every solution to the system consists of 4 numbers. I'm putting those numbers into a parentheses with commas between them. I have a number for x, a number for y, a number for z, a number for w. One thing that's really important here is that order really matters. We are assuming that the order is x, y, z, and w. That order has to be clear either from context or by use saying so, but if the order is clear, then this t minus 1 is x, this 2s is y, this s is z, this t is w. This line here is read such that, so the solutions are 4 tuples of the form t minus 1, 2s, s, and t, such that s and t are real numbers. So this is another way of presenting the solutions. Solving systems of linear equations is a mainstay of linear algebra. You want to be able to do small examples by hand, and you want to do enough of those until you're comfortable and it's just a chore. At that point, you can use computer software. Like my video if you liked it, subscribe to my channel if you want to be subjected to math videos, and keep hydrated at all times.